Alright, so a subset is pretty much exactly what it sounds like. If every element of S is an element of set T, then S is a subset of T. So let's just take an example real quick here. Let's look at the set of all integers, all one-digit integers, let's say. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, not 10 because it's one digit. And so we've got this set of all of these one-digit integers. Now, what are some subsets of this? Well, we could do 1, 2, 7, 9. That would be a subset. Oops, I don't like that. Alright, 1, 2, 7, 9 would be a subset. 3, 5, 2, I think you get the idea. These are all subsets because they include some of the elements that are in this larger set, but they don't have any elements that are not in the larger set. So like 0, 5, 3, 7, 4, 16 is not a subset because even though it has a lot of elements that are included in the set, it has some that aren't, like 0 and 16, right? Now let's take this set right here. 2, 4, 6, 9, 3, 7, 8, 5, 1. Alright, this is also a subset because even though it has the exact same numbers that are in the set up here, I'm going to call this set A so that we just know what we're talking about. So this set down here has all the exact same numbers that are in set A, and it has them in a different order, but it's still a subset because it doesn't have any numbers that are not in A. But it is different from these other subsets because these other subsets are all what we call proper subsets. So a proper subset means that if S is a subset of T and there is at least one element of T that is not an element of S, then S is a proper subset. So if we look at this set right here, for example, there are several elements of set A that are not elements of this set. There's the element 3, for example, 5, 8, you get the idea. Down here, 3, 5, 2, again, we've got 1, 6, 9, a lot of elements that are not elements of these set, even though there are no elements of this set here that are not elements of this set. Actually, this third set is not a subset. I shouldn't have circled that one there. Okay, this one here is not a proper subset because it has no element because there are no elements of set A that are not an element of this set. So the two sets are basically equivalent. So they're not proper. This one's, even though it's a subset of A and A is actually a subset of it, they are not proper subsets of each other. And let me just clarify that A is also not a subset of 3, 5, 2 or of 1, 2, 7, 9 because there are elements of A that are not in this. So the subset is, generally speaking, smaller, especially if it's a proper subset. If it's not a proper subset, then they're equal. Hope that makes sense. All right, now here's something really interesting, though. The notation for subsets I find really interesting because the notation for a proper subset is this nice little curve here, which looks a lot like the less than sign. And then the notation for any old subset, proper or otherwise, is this, which looks a lot like the less than or equal sign. So what do we notice about that? Well, the less than or equal sign, so let's think about what it means for a set to be a proper subset. If it's a subset, it's either going to have a smaller number of elements and be a proper subset, or it's going to have the exact same elements and be equal. So the notation for a subset kind of has this idea in mind that it's either a smaller number of elements or it's equal, whereas a proper subset is strictly a smaller number of elements. So that's a really good way to remember it, and it's kind of cool how these methods of notation correspond to one another. Oh, and then it says here that if S is a proper subset of T, then it has to be a subset of T, just like if 8 is less than X, then you could also say 8 is less than or equal to X and have that be true as well, right? But if I say 8 is less than or equal to X, that doesn't necessarily imply that 8 is actually strictly less than X. So that's just basic logic, right? All right, so let's look at a couple of examples of sets. Let Z, so we have a set called Z, be the collection of all the integers, and N is the collection of all the positive integers. So the interesting thing about this is that both sets are infinite, right? There's an infinite number of integers. And then we have all the positive integers. So one set is going to be 1, 2, 3, 4, 5, 6, etc. That's going to be set N. And then set Z is going to be, let's just say -6, -5, -4, -3. It's also going to include 0, and then it's going to include 1, 2, 3, etc. Let me move this over just a little bit. So in this case, even though both of these sets are infinite, we know that every element that is in N is also in Z, but not every element that's in Z is an element of N. So we could say that N is a subset of Z. We could also say N is a proper subset of Z, right? But we could not say Z is a subset of N. That would not be true. Here's another example they have. It says if Z is the collection of all integers, again, same set there, and then S is the collection of all numbers larger than 1 and less than 2.5. So let's look at that over here for a minute. We've got this set Z, and then we're going to make this new set S. Let me get rid of this stuff here. We've got this set S. All numbers larger than 1 and less than 2.5. So 1 is not included, but 1.0003 would be included. The number 2 would be included. The number 1.94, number 2.0056. There's an infinite number of numbers in here, but almost none of them are integers. 2 is the only integer that's actually in this set. So S would not be a subset of Z or of N. And Z would not be a subset of S either. So neither of these two sets is a subset of the other one. Same with S and N. Neither one is a subset of the other one. Because they include different terms, right? 5 is not included in set S. 1.94 is not included in set N. Alright, the last thing I want to point out is that the empty set is a subset of any set, which just means that if you have a set here that's completely empty, nothing in it, then it would be a subset of any other set. So it doesn't matter what you put in here. You could put 1, 5, -3, the color red, some guy named John. Whatever's in this set, the empty set is going to be a subset of that set. And sets aren't necessarily only numbers. Most of the time when we talk about sets in math, it's numbers, but set just means a set, a group of things. So you can have the color red, the guy named John, they can be in a set together. Maybe a set of all the things that begin with the letter R or J, but you could have a set like that.